Okay, so we're going to pick back up with discounting. So let's just start off with an example, right? So sometimes it's easier to deal with concrete numbers. So let's just use an example of the discount rate is equal to, let's say, 2/3. So what that means is, so what that means is that period 2 matters for the final payoff only 2/3 as much as period 1. And so more broadly, we would write pi sub j is equal to pi sub j in the first period plus two-thirds pi sub j in the second period plus two-thirds pi j in the third plus, and this thing can now go on forever. And so one useful fact that we're going to talk about in more detail shortly is that even though this is a sum of an infinite number of numbers, it turns out to be, when you add it all up, you add it all up and you find a finite number. So it's a little counterintuitive, and we'll talk a little bit more about the math. I guess that may be something that you've seen in a calculus class, but that's the idea. So, and then of course this was just an example of a discount rate. More generally, the discount rate is beta, with 0 is less than beta is less than 1. So we did the first example with beta is equal to 2/3, but beta can be anything. So let's do this. Let's do a quick example, just to sort of convince you that, yeah, you can actually add up an infinite number of these things, and it makes sense. So let's think about this. So let's think about adding up 1/2 to the 0 power, which of course is 1, plus 1/2 to the 1, plus 1/2 to the 2, plus, and we're going to keep going forever. So let's see. Let's just take this in chunks. So 1/2 to the 0, well, that's 1. 1/2 to the 0 plus 1/2 to the 1 is 1.5. 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 is, so this is 1 plus 1/2 plus 1/4 is 1 3/4. And so one thing that you may notice here that's sort of interesting is so that this 2 is equal to 2 minus 1/2 to the 0. That's just another way to write 1. It's kind of a strange way to write 1, but you're going to see that it's going to be useful. So 1.5, that's equal to 2 minus 1/2 to the 1. If we say this 1 3/4, well, that is equal to 2 minus 1/2 squared. And so the idea here is that as you so say, for example, if we added up 1/2 to the 0 plus ... plus all the way out to 1/2 to the k, where k is just some number, then, well, when we added all this stuff up, you can sort of see the pattern of how it's developing. This would just be 2 minus 1/2 to the k. And then as k gets really, really big, then this sum will approach, this 1/2 to the k power, if k is going to approach infinity, then 1/2 to the k power is going to approach 0. Because you're multiplying 1/2 by 1/2 by 1/2 by 1/2 enough times, you're getting smaller and smaller numbers. So this value will approach 2. And so the point here that I just wanted to illustrate is just that you can add up an infinite number of terms and end up with a finite number. Okay, let's see how this works a little bit more generally. So let's ask what is beta to the 0 plus beta to the 1 plus beta to the squared plus ... So this is just a more general version of the first thing that we wrote. Well, let's just write that, this, let's just say that equals x. Just, for convenience, let's give this thing a name. Well, one thing that we can say then is beta times, so this beta to the 0, so that's 1. So 1 plus beta times beta to the 0 plus beta to the 1 plus beta squared plus ... equals x. So this looks a little bit strange. I just want to talk through sort of how this step happens. So beta times beta to the 0, that's beta to the 1. Beta times beta to the 1, that's this beta squared, and so on, right? And so, the left-hand side of this expression is just equal to the left-hand side of this expression. Now, the reason why we're writing things down in this kind of strange way is that now we can replace this with 1 plus beta times x is equal to x, right? Because this thing inside the parentheses, that's x. That's what we found that's what we named it in the last statement. So now we just need to do a tiny bit of math. And so let's see, so this is 1 is equal to x minus beta x. 1 is equal to x, 1 minus beta. And so x is equal to 1 over 1 minus beta. By the way, I should have specified this in the beginning, but this is all assuming that 0 is less than beta is less than 1. So otherwise, this will actually not be true. But okay, so with the caveat that 0 is less than beta is less than 1, we can do this statement. So this is going to be something that we use quite a lot when we talk about infinitely repeated Prisoner's Dilemma. Okay, so I'm going to wrap up this video here, and I will see you all next time.